Okay, so we have our width from A to B. N value is 6. B minus A over N. We get 5/6. Okay. Now, next step is to find the x values of our subintervals. So x values of our subintervals. We're going to create a number line here. So for your number line, extend from endpoint to endpoint, so 0 to 5. That's your A and your B value will go here. We're going to create our subintervals, and each subinterval we're going to add with the appropriate width. So 1 subinterval, 2, 3, 4, 5, 6, right? So we have 6 subintervals here, 6 rectangle subintervals. So we're going to add 5/6 to every number and identify that value. So 0 plus 5/6 is 5/6. Plus 5/6 is 10/6. You can reduce the fraction if you like. You don't have to. And then we should end up at the last value here. So 25 over 6 plus 5/6 is 30 over 6. And 30 over 6 is the same thing as 5. Okay. I said not to worry about the graph, but the graph looks something like this. And we just have to figure out, which heights to use to build these rectangles. Right? So we have the first subinterval here, second subinterval, third, fourth. Okay, so for left sum, we're going to be finding the rectangles, width and height of each rectangle and adding them up. So area. We know that the width of our rectangle is 5/6. And now the height that we need is going to have to come from the left endpoint. So either we're choosing between f of 0 and f of 5/6, but f of 0 is representing the left height of our rectangle. So we'll say f of 0. Second rectangle has a width of 5/6 and a height of f of 5/6. Third rectangle, width of 5/6 and the height of f of 10/6. And we go down the line. Now, the only value that we don't use is f of 5, because f of 5 is the right right endpoint height of our rectangle. It doesn't represent the left height of any rectangle, right? So we use f of 0, f of 5/6. All right, and the last rectangle we use f of 25/6. We don't use f of 5 because it does not called for with our left sum. So this is right before we do the plug and chug portion, where we just find each of the heights by putting the x value into the function and grabbing whatever y value is, and then we can multiply and add all those values together. Okay? But I'm more concerned about getting to this point because the rest is just using the calculator. A way that you can maybe save a little bit of writing out all these widths is you could factor it out, and then it's the same width every time. So you just factor the width out and then just add up all the heights together. You can do it this way, or you can write it out individually, but just to give you an option if you want to save a little bit of writing. Okay, so any questions with this process here? All right, same idea for right sum, right-handed rectangles. Still the same interval, same function, same width, but now with each subinterval, we want to choose the height of the right endpoint. So for the first subinterval, I'll choose f of 5/6, f of 5/6. Second subinterval, I choose f of 10/6, all the way down, and the last one I choose is f of 5 as the height of the sixth rectangle. And now things are flipped because for right sum, we don't use f of 0, right? F of 0 is not going to represent the right height of any rectangle. Okay. And some of these I have their fractions reduced, but you can leave them unreduced and they mean the same thing. Okay, any questions with left sum or right sum? I also want to go over midpoint sum. So the way that we do midpoint sum is we have to find a little bit more information than the subintervals provided, because these subintervals are not giving us the midpoints that we need. So we have to spend the additional time to find the average between these two numbers so we can find that midpoint. So to find your average, you're going to add the two endpoints of your subinterval and divide it by 2. Which is the same thing as multiplying by 1/2. So 0 plus 5/6 is 5/6. Divided by 2 is same thing as times 1/2. So 5/6 times 1/2 is going to be 5/12. Okay. Same thing here. If I want to find the average of these two numbers, I add together, divide by 2, or add together, multiply by 1/2. So 15 over 6 times 1/2 is going to be 15 over 12. 25 over 12. 35 over 12. 45 over 12. And then 55 over 12. So we're going to take these x values and attach them to the function. So these are going to be where we're going to be finding our heights for each rectangle. So we can factor out the 5/6 as the width. We don't have to write the width every time. We can just add up all the heights individually. All right. So width times height, width times height, width times height. But to save time, you could, or save writing, you can just write the 5/6 out once. Okay, any questions here? I also want to go over trapezoid sum. So trapezoid sum, we talked about on Friday how trapezoids can be merged together, right? So we talked about how the formula for each trapezoid is 1/2 width times height 1 plus height 2. But when you add up all the different trapezoids, you have all these trapezoids that all share the same size, right? So the second trapezoid is going to be 1/2 width times height 2 plus height 3, right? And so every trapezoid is going to have a duplicated height. So one thing that we can do to speed up this process is we can just factor the 1/2 width out, and we can just add up all the heights and just understand that every height that sits between is going to appear twice. except for the very last one and the first one. The last and the first heights are only going to be used once because these are not shared, the ones at the end. There's no shared sides. So if we use that process, then we can do 1/2 times the height, sorry, 1/2 times the width, which is 5/6, and just write down all the initial x value subintervals that we had, right? We don't use the midpoints, right? Just the initial subintervals. So f of 0 all the way to f of 5, and then we just double all the middle heights. All right, any questions here? Okay. So we'll get a chance to practice these types of problems again on Wednesday, Thursday, but just want to make sure that we've seen these different types of situations from left sum all the way to trapezoid. All right, there's another way that we can find areas of rectangles, and that is given a table of values. And this is a very common way that AP exams, especially Riemann sums, involving Riemann sums, are presented as table of values. So we have to, so I want to talk about how this is an easy process. However, we have to understand all the details of this process. But once you get it, then you can apply it for every problem, and it'll be easy. But I'm also going to point out how if we don't learn it correctly, or if we make a mistake, it kind of snowballs for all the process, for all the problems that you're doing. So I want to point out those specific things at the beginning, because once you can get those basics down, then you won't make a mistake anymore. So the first thing we have to recognize is that these widths are not going to all be the same. Unlike the previous one, right? The previous problem, we're creating a width, a common width that is shared between all the rectangles. But here, the width is dependent on what you see in your table. So the width is going to be potentially different for all the rectangles. So first thing we need to recognize is we do not use the width formula. Okay, we use the width formula if there is no indication for the width, and we have to create our own width. But here the width is provided for us, so we're not going to go and build our own common width. So that's the first thing to recognize. Okay. So part A, it says give the middle approximation with 3 subintervals extending from 0 to 20. So sometimes the interval may not use every order pair for this table. So just be careful of that. In this case, it does, right? It extends from 0 to 20. So all the order pairs will be used for this, for our approximation. Okay. Just like before, we're doing Riemann sums, so our area is going to have a width component and a height component. But the way that we pull the width and height is very specific. Okay, so I want to go over that process. It says 3 subintervals. I talked about how the subintervals may not all have the same width, but every subinterval is going to span across the same number of order pairs. Okay. So we have 1, 2, 3, 4, 5, 6, 7. We have 7 ordered pairs. We have to draw the subinterval so that every subinterval sees the same number of ordered pairs. Okay. So we're going to be creating some brackets so that we can kind of separate and identify these subintervals. So the way you want to draw these brackets is you want to start at the center of your order pair, and you're going to extend to the center of your last order pair. Okay, don't start at the end. I see mistakes students make if they're drawing their brackets this way, and that just throws everything off. So make sure you start at the center and end at the center of your last order pair. So looks like each order pair or each subinterval is going to span across 3 order pairs. And when you draw your second subinterval, you're going to have shared order pairs. Okay, so you have a shared order pair and extend to the end of your second subinterval, and then shared order pair, extend to your last order pair. All right, so being able to draw the subintervals correctly is important, right? If you draw the subintervals incorrectly, it just throws everything off. All right, any questions here? Now, the width is going to come from this information that we have here. So the way we find the width, look at where your subinterval begins and ends, and find the distance between those two x values, and that is going to be the width of your respective rectangle. So in this case, 8 minus 0 is 8. That's the width of my first rectangle. My second rectangle, and that means the middle, if there's any middle values, we ignore it. Okay, we only see where the brackets end and begin, and that is the only determination of our width. Second subinterval, we start at 8, we end at 12. We want to find that width. That width is 4. 12 minus 8 is 4. And then our third subinterval, we extend from 12 to 20. That's a width of 20 minus 12, which is 8. So we have the width of each subinterval. Notice that there's no guarantee that they're the same. In this case, we have to find them all separately. Okay. Now the height information is going to come from your f of x, your y values. Okay. Now it says to use middle approximation. So let me talk about how these y values are used. If it's asking for a left Riemann sum, then we want to choose a height of 4. If it's asking for a right Riemann sum, then we want to choose a height of 3. If it's asking for a middle Riemann sum or middle approximation or middle rectangles, then you want to just choose whatever number that sits in between. Don't worry about finding the average. If 5 doesn't sit between, is not the midpoint between 0 and 8, we don't care. Okay, this could be sitting at 1 and 8 or 1 and 10. Whatever lands in between, it doesn't have to find the midpoint. So I think some students, they overcomplicate it. They want to find the average. So we don't do any of that. Okay, whatever number you see between is number you're going to use. So because I'm doing middle approximation, I'm going to pick the middle y value. Right. Doesn't have to be exactly between. And we're just using the table of these values. We're not going to create any other information than what's provided for us. So for my second subinterval, I see the middle y value is 7. And then for my third subinterval, I see my middle y value is 6. So now I have everything that I need in terms of the width and height. So first rectangle, width times height. Second rectangle, width times height. Third rectangle, width times height. Okay, combine those numbers together, 16 plus 28 plus 48, 92. So I think this is an easy thing to do, but I also understand how if you're not interpreting information correctly, or if you're thinking that midpoint is the average of two numbers, or you're drawing your intervals incorrectly, or you're not doing a shared endpoints for your subinterval, then it's easy to get thrown off, right? So it's easy, but it's also very specific, right? We need to have these steps down, otherwise it's possible that students miss every problem because they just have their information set up incorrectly. Okay, any questions so far? All right, let's do part B. Use right-handed rectangles to approximate the area. So right-handed rectangles, we're still using the same number of subintervals. We're still going across the same endpoint to endpoint. So that means our subinterval is going to stay the same. We're still using the same width for each rectangle. But now the difference is that we're going to be choosing a height that is in a different location. So we're no longer going to use the 2, the 7, or the 6. Okay. For each subinterval now, we're going to choose the height that is sitting on the right side of each subinterval. So first subinterval, we'll choose a height of 3. Second subinterval, we'll choose a height of 3. Third interval, we'll choose a height of 10. So 8 times 3, width and height for my first rectangle. 4 times 3, height of my second area of my second rectangle. And third rectangle, 8 times 10. Okay, any questions so far? All right, let's do, I'm going to go to this table on the back here, and I want us to do a trapezoid one. So I'm going to do part D, but I'm going to copy this down and move it up so it'll be, so we don't have to keep shifting the paper here. So 3 trapezoids from 3 to 17. Okay, 3 trapezoids from 3 to 17. Okay. All right, let's pay attention to our interval. We're not going to use all the ordered pairs. We're only going to extend from 3 to 17. And we're going to have to separate these intervals so that they all see the same number of ordered pairs, 3 trapezoids. Okay, so I'm going to start at 3. Looks like there's 7 ordered pairs here again. So I'll go from middle to middle, share the same endpoint, and then share the same endpoint of your interval. You see how each subinterval sees the same number of ordered pairs, and that's what we want. Okay, we have an area formula for trapezoids. Now, we can't use the trapezoid approximation where we doubled all the middle terms because all the widths is different. So we're going to have to find the area separately for each trapezoid. So we got to do this process 3 times, once for each trapezoid. Okay, we can't do the we can't double all the middle ones because the width is all most likely going to be different. Okay, so let's first find the width. So we find the width by subtracting, find the distance between the endpoints. The middle x value is not going to play an impact on us. So 10 minus 3 is 7. Now we can't, these is a coincidence, right? These are just a coincidence number. We can't think of that. This number is always going to be the width. Okay, 13 minus 10, that's a width of 3. Distance from 13 to 17, 17 minus 13, distance of 4, width of 4. Now for each trapezoid, we're going to be pulling two heights, okay? But just the ones at the end, just where your interval starts and ends. We don't care about the middle one. We only care about where your interval starts and ends. So my first trapezoid has an area of 1/2 width. My width for my first trapezoid is 7. And then I just want to pull the two heights, height 1 plus height 2. Okay, I'm done with my first trapezoid. I'm going to go to my second trapezoid, width of 3. And then 9 plus 2. And then width of 4, 2 plus 5. Clean all that up, multiply that out, and we get 83. Okay, any questions here? All right, good. Let's go to our notes for 4.1. First semester, we learned all about derivatives, right? We learned about first, once we started derivatives, the first thing that we learned was power rule. And then we learned about all these other different derivative rules. So this semester, we're doing the antiderivative process. We're undoing these derivative rules, and we're learning how to go back to where we came from. So all these derivative rules that we learned, we're essentially just going to be working backwards from all these rules. But going backwards has its challenges. There's more things to keep track of, and but just want to kind of make sure we understand the big picture. We're just undoing the process that we learned from first semester. So let's talk about power rule from first semester. For power rule, let's say we have x squared, right? The derivative for x squared, you would say, is just 2x. And the way you did that was you brought the exponent down in front, and then you subtracted 1 from the exponent. Right? The 2 came down, and then 2 minus 1 becomes 1, so you're left with just 2x. But let's think about the operations that we did, right? So the operations that we did was we multiplied, right? We brought the exponent down, so we multiplied. And then we took that exponent that we had and we subtracted 1 from the exponent. And then we're left with 2x, right? Now, let's say we want to go the other direction. Let's say we want to move from 2x back up to x squared. That means we have to kind of backtrack, and we have to do the opposite or the inverse procedure. So if I want to go backwards, if I want to move back up to x squared, instead of subtracting, I got to do what? How do we undo subtraction?
Add.
Yeah, so we're going to, instead of subtracting 1 from the exponent, we're going to add 1 to the exponent. And then instead of multiplying, we're going to be dividing. Okay, so let me just show you what that looks like. So if I'm starting at f prime, I should be able to make my way back up to x squared. So we're going to add 1 to the exponent. So right now, 2x is sitting at a degree of 1. So if I add 1 to the exponent, I get plus 1, which is 2. And then my new exponent is 2, so then I divide by that new exponent. The 2's cancel out. I'm left with x squared. So I'm back to where I started. Okay. So that is why we have integration power rule looking like this. Okay. We add 1 to the exponent. We divide it by that exponent. And something that is nice to see or to help us visually see that we're on the right track is whatever exponent you come up with here, you're always going to repeat that number below. Okay, so these numbers will always match. Okay. Now there's a couple of things here that you don't recognize, so I want to go through some of these notations. For antiderivative, we have this specific notation called the integral notation. Kind of looks like an F. The integrand is the value, the expression that you're trying to work with. You're trying to take the antiderivative for. Basically, this is sitting at the derivative level, and you want to move that up to a function level. Dx is really just notation. This is just telling us that our independent variable is in terms of x. All right. Now we've seen this notation before, right? If I say d over dx of 2x squared, this just means find the derivative of 2x squared with respect to x, right? We didn't do any calculation involvement with dx. We just know that is just part of the notation for derivative. So same thing here. We don't do anything with the dx in terms of calculation-wise. We just know that is there as part of notation. So when you go through, when we go through our antiderivative, so 2x became x squared. We went through this process, and we're left with the antiderivative. And then there's also a plus c that's going to show up. It's a constant of integration, and that's always going to show up when we take the antiderivative. Okay, so I want to talk about why there's a plus c each time we find the antiderivative that didn't show up when we took the derivative. Okay, so let's talk about that with this demonstration here. We have 3 functions here: x squared plus 5, x squared minus 13, x squared plus 126. So let me ask you this: what is the derivative of x squared plus 5? Just 2x, right? That 5 disappears. What's the derivative of x squared minus 13?
2x.
Also 2x, right? All those constants will just disappear. Okay, so let me ask you this. How many functions will share a derivative of 2x? What do you guys think?
Infinite.
Right. Basically, as long as it falls under a family of x squared, the constant can be any value. And so we want to kind of create an umbrella that represents all the possibilities that share the same derivative. So that's why when we take the antiderivative, we'll say 2x becomes x squared plus c. Because we can add a constant to any of these functions and still result in the same derivative. So the antiderivative of a function is going to be in the form of f of x plus c to show that, there's all these potential constants that all share the same derivative. Okay. All right, so that's why we have that plus c show up whenever we're going backwards with that process. Okay, so the process of integration is called anti-differentiation, or taking the indefinite integral. Indefinite integral results in the function, so we're going to be focused on this initially. And then later on, we're going to take this process and allow us to find an area-related information. And this is going to be a much more efficient way rather than going through the limit definition that we're going through currently with the summation formula and substitution and all that algebra steps. Okay, so once we get past that area formula, we're going to have a much more efficient way involving integrals, involving power rule. Okay, let's go to the next page. So I just want us to do a little practice with power rule for integrals. So again, the steps that we're going to apply is we're going to be adding 1 to the exponent. And then we're going to be dividing by the new exponent. Sorry. All right. This is a rule involving constants. I'll get to this when we see a problem like that. And don't worry about this last rule right now. We're going to revisit that later, or come to that later. Okay, so think about, let's think back on with our first semester. We talked about how power rule for derivatives is the one that we use the most often, right? But it comes with conditions. We can't just do power rule anywhere we see a variable. We have to make sure that things are in place. Otherwise, power rule is not going to, otherwise our process is not going to result in the answer that is correct. So a couple things we have to make sure is before we apply power rule, we want to make sure that is there rational exponents that is sitting there, or is it radicals? If we see radicals, we got to convert to rational exponents. If we see variables in the denominator, we got to move it in the numerator. And if we see any parentheses, we got to make sure we expand. Okay, so we need to resolve and expand all parentheses first. If we want to do power rule. So the same conditions will apply for antiderivatives. Okay, these things have to be set in place, just like how we did with derivatives. Okay, so let's start with some easier ones, and we'll work to ones where we have to play with these conditions. So number 1, 7x dx. Again, the integral and dx are just notation. We just know that they will always sit there. But really, our work is really just done with this 7x here. So it looks like every condition is ready to go. There's nothing that is standing in the way of us being able to see this problem clearly. So now we're going to jump into our antiderivative rule, our power rule. We're going to add 1 to the exponent. So right now, the x is sitting at a degree 1. So we're going to add 1 to that exponent. Keep the coefficient. And then we're going to divide by that new exponent. Something to keep in mind visually is these numbers will always match. Okay, whatever exponent you create here, you're going to copy that same number below. And then we have a family of functions that all share the same derivative, so we need to have that plus c. Okay. You can write it this way, or you can push the coefficient out in front. Either way is fine. Okay, let's skip down to number 3. I have 3 terms. No issues here, right? No radicals, no denominator variable, no parentheses. So it looks like we can apply power rule to each term separately. 2x to the first power, I'm going to go through power rule here. Add 1 to the exponent, divide it by that new exponent. Add 1 to the exponent, divide, add 1 to the exponent, and divide. And then plus c. Now, I had some students ask me about, well, if these are all separate terms and if they all produce a plus c, shouldn't this be a plus 3c? Right? And to answer that question, yes, you can make an argument that this is plus 3c, but c is a number that represents a constant. And if I do 3 times a constant, I'm still left with a constant, right? So we just kind of make this 3 just kind of get absorbed into that c, and we only have to write a plus c once, because technically they all produce a constant, but we can kind of just push it all together and just call it a constant. Okay, clean this up a little bit here. All right, questions so far? All right, let's look at number 4, and then we'll end with 5. Okay, so number 4. No radicals, so we're good there. No variable in the denominator, we're good there. But we have some parentheses that's standing in the way, right? We got to spend the time to expand these parentheses before we can get a clear picture of our power rule. So this is expandable. Combine my middle like terms. And now I'm going to set up my antiderivative. Everything is set up and ready. All of our conditions are good to go. Now I want to revisit something here. Notice that every degree rose by 1, right? So 1 became 2, 2 became 3, 4 became 5. So we got to get into the mindset that when we take the antiderivative, your degree is going to rise by 1. Okay. All right. So 9x squared becomes 9x cubed over 3. 6x becomes 6x squared over 2. So let me ask you this. What do you think is going to happen to 1?
It becomes x.
Say it again.
It becomes x.
Good, becomes x. Okay, let me talk about y here. This is really x to the 0 power, right? X to the 0 power is just 1. But having that there may be helpful for you to see, because really we're increasing that degree from 0 to a degree of 1. So 1 constant becomes a linear. And the reason why I want to point this out is because I think a lot of times we're still stuck in the mindset of derivatives, and it's easy to think of that 1 and make it go to 0. Right? That is true for derivatives, but with integrals, we're going the opposite direction, right? So a constant is going to rise up to be a linear.
Mr. Yang?
Yes.
I thought the denominator was supposed to be
yes, so, okay,
like
so let me finish this process here. So here, x to the 0 power, we add 1 to the exponent, so it becomes x to the first power over 1. And that's the same thing as just 1x, right? So if I have a denominator of 1, I can just make it drop out. Is that what you're asking about?
No, I was asking about 9x cubed. Like why the denominator isn't 9? Like why 3 instead of 9?
Oh, okay. Because we want to match the exponent with the denominator. So the exponent and denominator will always match. So you see how these numbers match? So it's the exponents that match.
Okay.
The coefficient is just going to hang out in front. Oh, okay, yeah. So all right. So it's a coincidence that these are the same, but it's not.
Okay.
There's no correlation here. We're looking at the exponent and the denominator.
Okay, that makes sense. Thanks.
Yeah, exponent and denominator will match. Okay, reduce. Good. Any other questions with 4? Okay, let's do one more, number 5, and we'll be done. Now, number 5 is a little bit more involved because we have 3 potential issues here. There's a radical that we have to resolve. There is a denominator variable that we have to move. And when that variable gets moved, there's going to be some parentheses we have to resolve. Okay, so we have 3 things we've got to deal with here. First thing, I'm going to deal with that denominator and that radical. I'll rewrite that as x to the 1/2. And then that x to the 1/2 has to be pushed up. So when I push that exponent up, I got to change the sign, but I got to also make this division problem into a multiplication problem. So we got to make sure we protect that numerator with the parentheses so we don't forget that this has to multiply with everything in the denominator. So here's my cleanup effort here. If I move that denominator up, I got to change that exponent from a positive to a negative. So our first 2 issues have been resolved, radical to rationals, denominator to the numerator, but we still got to take care of those parentheses. So I'm going to distribute the variables through. Right now, this x is sitting at a degree 1, so we can't do power rule until parentheses have been removed. So we got to distribute this through. When I distribute, I'm going to be adding exponents. So 1 minus 1/2 is 1/2. One times anything is just itself, that term itself. So now we're sitting in a place where every condition is set up and ready, and now we can apply power rule. Okay, so with power rule, we add 1 to the exponent. So plus 1 is same thing as 2/2 if I want to match the denominator. Negative 1/2 plus 2/2 as well. So 1/2 plus 2/2 is 3/2. So whatever exponent I create, I'm going to copy that same number below. My new exponent is to the 1/2. And then plus c. Now I want us to do a little bit more cleanup here. Whenever I see a complex fraction in the denominator, I'm going to flip that up and to the numerator, but I got to change the order here. So if I'm dividing by a fraction that's multiplied by the reciprocal, so I'm going to push that 3/2 as 2/3, and I'll push the 2 as the 1/2 as a 2. Okay, any questions here? All right, we'll practice with more of these problems tomorrow. We'll need to finish up our 4.1 with trig derivatives. Trig integrals. But I'll also be available this afternoon for help session, just going over these material that we did today, Riemann sums with common widths, Riemann sums with table of values. If you want to get more practice with the power rule, we can go over that this afternoon as well. All right. Wednesday, Thursday review, and then Friday quiz. All right.
Thanks, Jen.
Have a great day. See you guys.
Thank you.
Thank you. Bye.
Yeah.